Welcome back everyone. In this lecture, I will tell some more results about normal subgroups. Let us begin with one of the characterization. So, I will leave this as exercise. So, we have seen many characterization of normal subgroups. So, here is one characterization using commutator of elements. So, we say let us start with n being a subgroup of G. So, then n is normal in G if and only if. So, you look at the commutator of any two given elements, okay, n comma G. So, this is by definition n G n inverse G inverse, or one can also write it in other way, not a problem, n inverse G inverse. So, this you consider for all n in capital N and G in capital G. So, this should be an element in capital N. Okay. So, by normalizing property, okay, this normalizer, so we will come to that later. The normal subgroup by definition, if you will take this conjugation of any element G n inverse G inverse, so that should be an element in capital N. And since n is already in capital N, so the product of these two elements should be in N. So, one way is obvious. So, we are saying that this is also one of the characterization of normal subgroups. So, this is something I am going to leave it to you to actually verify. So, now this also actually can be reinterpreted in terms of is commutativity of two elements. Okay. So, up to this subgroup capital N. So, maybe like so I will write down the exercise, maybe this is first exercise. So, the second exercise again it gives characterization of normal subgroup in terms of the commutativity of two elements up to this normal subgroup N, okay, up to the subgroup N. So, that means if GH is in capital N, so then we should have if and only if. So, this is the statement HG should be in capital N, and this should be true for all GH in capital G. Okay. Whenever the product of these two elements are in capital N, so then the reverse product also should be in capital N. So, this is something I will leave it to you to check. Okay. So, we already defined the center of G. We saw that they are all normal subgroups. Center of a group is a normal subgroup of G. So, we have also seen some examples of some subgroup they are not being normal. For example, so this is something I will leave it to you to verify. So, if you take this particular subgroup H generated by this 2 cycle 1 3. So, this is identity and 1 3 inside S 3. So, this is a subgroup. Okay. So, because the order of this 2 cycle is 2, if you square it you get identity. This is basically subgroup generated by this 2 cycle 1 3. So, this is a subgroup inside S 3. So, what one can prove, this subgroup is not normal. So, this H is indeed not normal in S 3. Okay. So, for example, I will give you very explicit element, I will leave it to you to check. So, check that if you take this particular element G, which is 1 comma 2 inside S 3, and then if you look at the conjugate of this capital H with respect to this GH G inverse. So, this is not going to be part of H. Okay. So, this is something you can verify. So, you may wonder, is there any like way to get normal subgroups in general? Okay. Like I said, normal subgroups they arise naturally as kernel of some homomorphism, but again one can actually give some necessary condition or sufficient condition for some group being okay, some subgroup being normal. Okay. So, let's do one small proportion. Okay. So this is somewhat some elementary fact. So this is something one can generalize further, but later we will see how to generalize. But let's now look at only the condition. So if you assume G to be a finite group, okay, let G be a finite group, and let H be a subgroup of G which has index 2, okay, with index. So G H, this bracket is 2. So that means there are only 2 left cosets of H inside G. Okay. With this condition, one can prove that H must be normal inside G. Okay. So note that 2 is the smallest prime number. Okay. So it means, so the index of any subgroup divides G. Okay. So in particularly this index of this subgroup H in G is the smallest prime divisor that dividing G. Okay. So this actually motivates us to actually look for replacing this 2 by some prime number P, and then look at a subgroup of H, a subgroup of G which is H, whose index is P, where P is the smallest prime divisor of G. One can ask whether that subgroup is normal in G or not. It is indeed true, we will prove it later. Okay. So this is just an aside. So this can be generalized. The general statement is as follows. So if H is a subgroup of G and the index is P, where P is the smallest prime dividing this order of G, so then H should be normal in G. Okay. So this is something I will prove later, but let's look at what happens to the index 2 case. So here is the proof. So what we need to prove, there are many characterization of normal subgroups. So let us see, for given element G in capital G, the left coset of H must be same as right coset of H. Okay, this is the claim. So how one can prove? So because we have the one-to-one correspondence between the set of all left cosets of H in G and set of all right cosets of H in G. So the index 2 captures the number of left cosets as well as right cosets. So in particularly, if you partition G with respect to the left cosets, you get first H, which corresponds to the identity, and then disjoint union GH, because you start with G which is not identity. When G is identity, then this statement is obvious, so we don't need to worry about it. So if G is not identity, so then one can also, so one should start with non-identity element which is not in H. Okay. So if you take some element G which is not in H, then GH is not equal to H. Okay. So this implies immediately GH is not equal to H. So in particularly H and GH, they form a disjoint left cosets of H in G. Similarly, since again G is not in H and H will be not equal to HG, so again you get the disjoint union of right cosets H disjoint union HG, because there are only 2 right cosets and 2 left cosets, and these are the two of them. So now you can see that from purely set theoretic point of view, G is partitioned into some A union B1 and A union B2, where A and B1, okay, A B1 they are disjoint and A B2 they are disjoint. Okay. So G you have partition like this. So then this immediately implies B1 equal to B2. So, that means Hg is same as Gh. Okay. So, only these two cases are possible, either G in H or G not in H. When G in H, then for G in H we have GH equal to H, and as well as Hg equal to H. Okay. In that case, this is verified for free. So, you take element which is not in H, then we have verified that this is what happens. So, this means if you know for some reason a subgroup has index 2, then immediately you can conclude that that subgroup must be normal. So, this is actually very interesting result, and this is used many times in order to understand groups of orders, small order. Okay. So, these things it will come later. So, we will actually keep using this. As I promised, I will also prove this general statement later once I introduce more tools. Okay. So, we have seen some normal subgroups, okay, and as well as some subgroups not being normal. So, now the notion of this normal is actually carried out when you take intersection of subgroups. So, that is something very clear. So, let me write it as proportion. So, this proportion in particularly allows us to actually talk about normal subgroup generated by some subset of capital G. Okay. So, let me write first of all what is the proportion. So, I will write it for any collection, but one can do it for just two normal subgroups, not a problem. But the same proof works for any collection. So, let us start with a collection of subgroups. Okay. So, if Hi, so this is a collection of normal subgroups of capital G. Okay. So, then we can look at the intersection. We have already seen that the intersection of subgroup is a subgroup. So, now we are looking at intersection of normal subgroups. What can we say about it? And this also must be normal in G. So, what is the proof? Proof again is very easy. You start with some G in G and X in the intersection. Okay. So, we will prove that the conjugate of this X by G, that must be inside this intersection. Okay. Look at the conjugate. Okay. So, since Hi is normal, so this is going to be inside Hi for each I in I, as Hi is normal in G. Okay. So, in particularly this GH G inverse is going to be inside the intersection of all I. So, that means we proved that G, this intersection Hi I in I, G inverse is subset of intersection Hi I in I. Okay. So, this is one of the characterization of normal subgroups. So, that is something verified now. Okay. So, now let us see how it actually leads to the definition of normal subgroup generated by some subset. So, here is the definition. So, you start with some subset of G, call it capital S. Okay. So, we already seen what is subgroup generated by capital S. Okay. That is, if you recall, one way to define it, you collect all subgroups of G that containing S and then take the intersection of them. Okay. That is the subgroup generated by capital S, which is also the smallest subgroup, okay, with respect to the inclusion that contains capital S. So, motivated from that, you can easily see that if you are interested in looking for the smallest subgroup that contains S with respect to inclusion, okay, or smallest normal subgroup, then all you do is collect all the subgroups. Let us call it Hi, okay, H, where H is containing S, H is normal in G. Look at this collection. Okay. So, this is some collection. Then what you can do, you can take the normal subgroup generated by S, so which we denote it by bracket as normal. So, this is just take the intersection of all these groups coming from this collection I. So, take all intersection of all subgroups, normal subgroups of G that containing this S as subset. So, that is the definition of normal subgroup of G generated by capital S. Of course, this is defined theoretically. So, you may wonder why one will be interested in something like. So, this is actually very important in order to define what is called presentation of a group. Okay. So, for example, you must have seen in textbooks, many textbooks, the dihedral group that is actually defined using a presentation of the dihedral group. Okay. So, it is generated by some symbols A comma B such that A power n is identity and B is involution, B square equal to identity. Okay. So, such definition makes sense once we know what is presentation. Okay. In order to define what is presentation of a group or group generated by some set of generators modulo some relations, we need to first define what is called free group, and then we need this notion of normal subgroup generated by that capital S. So, let me just briefly tell you what is the definition of a presentation, but in this we still need to define what is called free group generated by some set X. Okay. So, we will come to that later after maybe finishing whatever content that I am planning to finish in this course. Okay. But I will dedicate some one lecture in order to discuss about the free group. Okay. But what is presentation of a group? Okay. You start with the group, it is okay. So, let us say G is a group, and we want to say that G has this presentation. So, which is let us say generated by some set of generators, let us call that is capital S modulo set of some relations. So, this is called the set of generators and this is called the set of relations. Okay. So, for example, like I said, so if you take for example S3, okay, so and then you can take these particular elements sigma 1 2 and then tau 2 3. So, then S3 has this presentation. So, it is generated by sigma and tau such that sigma square tau square is identity, and then sigma tau, okay, I guess power 3 should be identity. Okay. So, this can be rewritten as follows sigma tau sigma. So, basically sigma tau power 3 is identity. So, then you can write sigma tau sigma tau sigma tau is identity. Okay. So, let me use identity as E. So, then this can be rewritten. So, if you keep this sigma tau sigma, which is same as tau sigma tau, because sigma inverse is sigma and tau inverse is tau using these two first relation. So, this is called what is called bride move, okay, bride relation. But anyway, so this is something you can verify once I define what is presentation of a group, okay, but I am just giving you some heads up. So, what do you mean by, okay, given a group, what is the meaning of it is generated by some set of generators modulo some relations. So, basically this S you pick it up from capital G only as in that example, and then what you do, you take the free group generated by S, okay, this is the free group generated by capital S, okay, that means the only thing that you actually put. Okay, there should not be any relations. For example, in the finite group, if you take any element, then x power order of G must be identity. Okay, that is a relation. So those kind of relations should not happen in the free group generated by capital S. Okay, so it is generated by elements of capital S as freely as possible. So no relations should happen. So relations means it is just a product of some element being identity. So this is called relation. Okay, so such things should not happen inside your free group. Now what is the meaning of G is given by the set of it's generated by S and modulo the relations R. So generating is clear. You take the subgroup generated by S, that should be capital G. So that is what generating means. What is the meaning of it is given by generating by this modulo some relations. So that means you will be able to define this group homomorphism from f of s to G, because G generated by capital S, and then whose kernel, okay, so let us call this is pi, this kernel is actually going to be generated by these elements of capital R. Okay, this R is indeed coming from f of s. So f of s elements can be thought of as words formed from alphabets coming from capital S. So capital S are some collection of elements. Okay, you can form a word like this. Okay, and then any element of capital F of S can be viewed as word in S union S inverse. So anyway, so you have some set of words, and then what you demand mathematically speaking. So this G is isomorphic to this f of s modulo the normal subgroup generated by this capital R. So that is the meaning of G being generated by some set of elements S modulo the relations R. Okay. So let me repeat what you have. So given S, you have f of s, which is the free group, and you have this capital R, which is subset of f of s. Okay. So then f of s modulo the normal subgroup generated by this capital R should be isomorphic to G. So the quotient makes sense. Once you have a normal subgroup, we already seen that the quotient makes sense. So that quotient you demand to be isomorphic to capital G. So this is already kind of tells you that, okay, presentation of a group is not unique. Okay, you can have many different set of generators, and of course once you choose one particular set of generators, the relations will be depending upon the set of generators that you choose. Okay. So these things, as I promised, we will discuss it later, but you can see that this normal subgroup generated by some subset plays an important role when it comes to a presentation of a group. Okay. Okay, so let us move on. So here once we define this normal subgroups, one can immediately define what is called a simple group. Okay, this is again very important notion. So a group is called a simple group if it contains no proper non-trivial normal subgroups. Okay. What is the meaning of that? So you know that this identity subgroup, okay, the singleton identity is a normal subgroup. So that is easy to verify, and the whole group G, that is also normal subgroup. Okay. So a simple group that has only these two as normal subgroups. So none of other subgroups are normal. Okay. If identity and G are the only normal subgroups of capital G. Okay. So, this capital G which is called simple group, it has only these two subgroups as normal subgroups, and they are normal subgroup, that is trivial thing to verify. So, this is something very important notion, okay, because even in finite group theory, okay, so one of the important problem of finite group theory is classifying all groups of order given order. Let us fix some n, a natural number, okay, and then one can ask how many, okay, not how many, there will be, okay, that is also a very important question. There are two questions that are important. So, given n in n, okay. So, now one can ask how many groups of order n are there, of course up to isomorphism, okay. And we will see later that this is indeed a finite problem, okay, this has finite solution, and of course it is still wide open how many groups of order n are there for given n. And then once we know, so because we know that this is actually has finite answer, so one can immediately ask that how many groups of order n are there up to isomorphism, like what are all, can you classify, okay, can we classify all groups of order n up to isomorphism. So, these two questions are very big questions, that is what drives finite group theory, okay. So, but one can after learning sophisticated languages in group theory, one can see that any finite group can be built from what is called these simple groups, okay. So, the basic building blocks of the finite groups are simple groups. Of course, the way you build, okay, so every time you have to take extensions of some simple groups and so on, and then you can, using that only you can build general group, okay. So, but these extensions becomes very complicated. So, when you take so these things maybe I will discuss a little bit at the end of the course, okay. But given two simple groups, if you look at all possible extension of those two simple groups, that is not something easy to understand, okay. Even this becomes complicated problem even for abelian groups, okay. If you start with finite abelian groups, look at all possible extensions, so that becomes somewhat complicated problem. So, if you use finite abelian groups or finite simple groups to build some groups, so that will be called solvable groups. Again, theory of solvable groups is vast. So, you all must have known about the classification program of these finite simple groups, okay. So, you can actually read that in Wikipedia. So, I will leave it to you. So, maybe I will dedicate one lecture in discussing something about the classification of finite simple groups. Let us not do it now. So, here is one simple fact which is again very easy to verify. So, I will leave it as exercise. If you look at Z modulo n Z, okay, this is simple if and only if n is prime, okay. When n is prime, it is cyclic, and then you can see that if you start with any non-identity element, that will generate the Z modulo n Z when n is prime. And when n is not prime, if it is composite number, we already proved given any divisor, proper divisor, we will have a subgroup of order that divisor D, okay. So, that means, so since it is abelian group, okay, so any proper subgroup will become normal subgroup, okay. If it does not have any proper subgroup, then it must be, okay, corresponding to the prime number. Okay. So, here again I will give another example of not normal. So, these are all again comes for free, okay, if you understand the symmetric groups. So, if you take this again 2 cycle, sorry, the product of 2 cycle, which is order 2 element inside S4. So, this is not normal in S4, okay. And so, here is one more example which is again normal. So, it is the group of upper triangular matrices inside GL2R or GL2C. You take A, B, C, where A, B, C are, let us say, complex numbers such that the AC should be non-zero because the determinant should be non-zero. So, then this is actually a normal subgroup or not. So, maybe you can check. So, check this. So, this is a subgroup, that is clear, okay. So, let me just leave it to you to check whether H is normal or not in G, okay. So, what is G? G is GL2C. Okay, so this is all about some properties of normal groups. Okay, so later what we will prove. Okay, this is indeed a theorem. So we will actually prove it later. So we have already seen that AN is actually a normal subgroup of Sn, because that can be realized as kernel of this sign map. Okay, so we will see that for n greater than or equal to 5, AN is the only normal subgroup of Sn. Okay. So, this is something we will see, and as a corollary we will have that AN is indeed a simple group. Okay. So, AN for n greater than or equal to 5, it will be actually a simple group. And here we already have another family Z modulo PZ. So, this is indeed a family of simple groups. Okay. So, in this lectures, so you see that these two families, they are simple groups. Okay. Again, there are many interesting family of simple groups that comes from the theory of Lie groups. Okay. So, we will not actually, so I will briefly explain when I discuss about the classification of finite simple groups. I can't get into the too much detail because they are all too technical, okay, but I will discuss about that maybe at the end of my lectures. Okay, I will stop here, so we will continue later. Thanks.